Good evening. I would like to thank the organizers for the opportunity to present my data on the effects of aging on lateralized auditory processing. You have heard already a lot about auditory processing asymmetries in previous talks today. So mainly about that speech processing in most people is strongly left lateralized. There exist several other processing asymmetries, for example, that the left auditory cortex has a higher temporal resolution and the right auditory cortex has a higher spectral resolution. You have already heard about that this processing asymmetries does not only depend on bottom-up stimulus properties, but also on top-down effects, like do participants tend to the stimuli, do they have the task, do they have any experience with the task. When you think of the processing of complex stimuli like speech or music, then you need both the high temporal resolution of the left auditory cortex, but also the high spectral resolution of the right auditory cortex. So this means for processing of the everyday auditory environment, you need both hemispheres, and these hemispheres has to work efficiently together. If there is a dysfunction of this interaction, this might lead to deficits in auditory processing. This is the case, for example, in people with central auditory processing disorders or in older adults, maybe due to a reduction in the anatomy, for example, by a reduced myelinization. The aim of the present study was to answer the question, how does the involvement of the left and right auditory cortex change with age? For the investigation of lateralized auditory processing, we use the contralateral noise procedure. During this procedure, we present the task-relevant stimuli only on one ear, so on the left and on the right ear, and in half of the cases, we present contralateral noise. When you look at the example on the left side, when we present the task-relevant stimuli contralateral to the task, the main task processing side, then due to the contralaterality of the auditory system, the information directly arrives at this hemisphere where the task processing takes place. In the right example, when the task-relevant stimuli are presented ipsilateral to the main task processing side, then the information about this stimuli mainly arrives at the other hemisphere. And for task processing, the information has to be used from the weaker ipsilateral input or from the information transfer via the corpus callosum from the other hemisphere. If we present the left example noise on the contralateral ear, then the noise mainly arrives the other hemisphere and does not interfere with the task processing. If in the right case, we present contralateral noise contralateral to the main task processing side, this information of the noise directly arrive there and interfere with the task processing. And this interference we can observe by an activity increase with functional magnetic resonance imaging. We can also have with this procedure look what happens if there is a disturbance of this hemispheric interaction in any way. So in the right example, we would expect that the activity increase is even larger because there's a lack of this transfer of information from the other hemisphere. So what we do during this procedure is we compare the conditions without noise with the conditions with noise, and we look where during the presentation of ipsilateral task-relevant stimuli the activity increase. And from this activity increase, we infer the main location of the task processing at hand. For the current study, we measured two groups of participants. In one group, the participants were younger than 40 years. In the other group, they were older than 55 years. And all these participants were measured with visual function magnetic resonance imaging experiment to determine their language lateralization. So all these people had a left lateralized language processing. For one of the tasks, the so-called categorization task, we presented linearly frequency modulated tones to the participants in a block design. And the task for the participants was to differentiate whether the frequency was modulated downward or upward. This is important, for example, when you differentiate a question versus a statement. During a question, in the end, the frequency of would rise, whereas it will not during a statement. For this task, it has been shown that this is strongly processed right lateralized. This is not only the case in humans, but it has also been shown, for example, in rodents. In the next slides, you will see always such slices through the brain. And here the blue cycle shows you the area roughly of the auditory cortex. Now, when we come back to processing of speech or music, what you hear is always a sequence of your auditory environment. And what you do when you hear something is not to determine for each part of the auditory environment the frequency or the intensity or the length. What you rather do is you compare, for example, the frequency between different parts of this sequence. For example, you would say, okay, the third note is higher in frequency than the second note, or the last note here is longer than the previous note. So this is something you do always during, listen to your auditory environment. To simulate this situation, the participants had a second task, the so-called comparison task. Here they had to compare the direction of frequency modulation between the tones. So they had to compare whether the direction of the current tone was same or different to the previous tone. So they had to compare the third with the first, the second with the first, and the third with the second, and so on. So what you do during this is you always update your reference in memory. So this is a task that strongly requires working memory. For this task, we have shown that both auditory cortices are strongly involved. So the right auditory cortex is probably still involved because you still have to categorize the direction of frequency modulation, and the left auditory cortex probably gets involved because of this sequential comparison you have to do. This is in line with several previous studies that have shown that sequential processing in the auditory domain is also a left hemispheric task. So as this task requires both auditory cortices, it also requires a stronger hemispheric interaction than the other task, the categorization task. And our hypothesis was that this task is more difficult for older adults due to a reduction in the hemispheric interactions. Before we have done the fMRI experiments, all the participants did a psychoacoustic experiment, and we adjusted individually the task difficulty by changing the frequency range or the length of the tone. We did this because we have shown in a previous study that the task difficulty strongly affects the lateralization of processing of these two tasks. And I should also mention that the data I show you today are part of a bigger study. So all the participants solved each task at least 3 times. And you see today mainly the results of the first measurement for each task for each participant. In this diagram, you can see that the performance of the 2 groups, so of the younger group in blue and the older group in white, were similar between the groups for each task. What you can also see is that the comparison task was more difficult for both participants groups. This was because this addition of sequential comparison, and each participant had the same heard the same stimuli for both tasks. But I have to mention that although the performance was similar between the groups, the older participants had on average easier stimuli to differentiate. Here you see the results of the categorization task for the younger participants. What you see here in orange is already the increase due to the contralateral noise. And what you see is that in contrast to the hypothesis, both auditory cortices are already involved in the younger participants. This is probably due to the fact that all participants know before the other task, and half of the participants already trained the other task. But what is important or interesting is that when you look at the results of the older participants, you can see that the activity increase due to the noise is stronger in the older participants. This means the older participants need more resources in the auditory cortex to solve the task, although the performance was similar between the groups. For the comparison task, you see in the younger participants that there is a left lateralization of processing, probably due to the fact that the sequential comparison was difficult. And most interesting is that in the older participants, there is a very strong effect of the noise, so stronger as for the younger participants, and this effect is even stronger than during the categorization task. So this means that during this task, from which we know from before that it strongly requires hemispheric interaction, the older participants need more resources in the auditory cortex. And this is also reflected in a stronger effect of noise in frontal and parietal regions that are responsible for attention and working memory. And this especially in older participants during this comparison task. To see whether we have really an indication of a reduced hemispheric interaction in our participants group, we did diffusion tensor imaging. And what you can see here in this diagram are the so-called fractional anisotropy, so a measure of the directionality of water. And this is the result of the area, the posterior area here in yellow of the corpus callosum. So this area where the fibers between the auditory cortices mainly cross the midline. And what you can see that this measure is lower in older adults. And this is an indication for a lower myelinization in this group, or a reduced number of fibers in this area. We then specifically looked at the fibers that connect to auditory cortices, and you can see that here the difference between the groups is even larger. So to sum up, I have shown you today that in older adults, there is a stronger involvement of the auditory cortex during task processing, especially during the comparison task. And we see also effects in frontal and parietal regions. So this means for the same performance, older adults use more resources for task solution, especially when hemispheric interaction is strongly required. We have also seen specifically for our participant group indications for reduced myelinization and a reduced number of fibers in the corpus callosum in the older adults. And this hints to a reduced hemispheric interaction in these people. And this might lead to more difficulties during processing of complex auditory stimuli. And this comes into addition to the peripheral hearing loss, which most of the older adults have. In the end, I want to thank all the people who were involved in the study and you for listening.
Thank you very much. Any comments, questions? Apparently not. Apparently everything was crystal clear. Well, I can ask perhaps one question. Did you consider looking also on connectivity measures between the two groups?
At the moment, yeah. So we're doing this at the moment, but we haven't any results yet.
If there are no other questions, then we just move on. Also given the time. So thank you very much again.